In this video, we will go over a kind of convolution called transposed convolution. Sometimes it is also called deconvolution, but I don't like that term because it is misleading. The right term is transposed convolution, but whenever you hear the word deconvolution in the context of neural networks, it actually means transposed convolution. On the other hand, if you're working with signal processing, deconvolution means to remove the effect of convolution, and that is a completely different concept than what you're going to hear, and that is why I don't like the concept being called deconvolution. This is transposed convolution, and in signal processing, when you want to restore the original signal, it is called deconvolution. And the original deconvolution is actually something people do. For example, if you have a blurry image which is obtained by, your camera actually shook and took a blurry image, in that case you can restore the original image if you know the convolutional kernel that produced the blurry image, and you can do deconvolution to obtain the original image. But what we are going to show now, that is not the same deconvolution. This is transposed convolution, but sometimes people call it deconvolution as well. So just be aware of this distinction. So we already know what convolution is, but let's go over the concept one more time. Now I'm showing here an input image which is 4 by 4, and I have a convolutional kernel which is 3 by 3, and I have put in some arbitrary values in there. To calculate the convolutional output, what we do is we take this kernel and put it in this orange area, and then we multiply all the elements by element and add the resulting numbers together to obtain our output, which is 53 in this case. And we can keep going. To calculate the next value of the output, we shift the kernel, and we do that for this third value and the fourth value. So now we have obtained the full output using convolution. So this was the input, we have this kernel, and this is the output we obtain. So one thing to note is that when we did this convolution operation, it actually reduced the size of the image. We had an input image, we applied a kernel to it, and the output is smaller than the input. Sometimes we want to do the opposite. We want to use some sort of convolution to increase the size of the output. And that is exactly what transposed convolution is used for. It is used to increase the size of the input image given a kernel. So how do we do it? So suppose this is the input. Remember that we want to have an output which is bigger than the input. We have a 2 by 2 input, and we have an output that shows up here. So the first step is we take this value 1, we multiply it with all the values of the kernel, and we put it on this output. Let me show you right here. So we took this 1 and we multiplied it with all the values of the kernel, and that's what goes here. Now think about it as one matrix. The second matrix is generated when we go to this 2 and we multiply all the values of this kernel by 2 and we put it at this location. Similarly, we go to the value 3 and we multiply it with all the kernel values and put it right here. And we do the same thing with 4. And now we have these 4 different matrices, and they all obviously have some overlap. What we do is wherever there is an overlap, we simply add the numbers together. Let me show you an example. For example, the second one is 3 plus 2, and all others are 0. See? So 3 plus 2 goes here, and there are other numbers where there are multiple overlaps. For example, for this cell, we have to calculate -1 plus 10 plus 9 plus 4. So that will give the value for this cell. And if you look at the final numbers, this is what a transposed convolution looks like. And what we have done, we have upsampled this image, this 2x2 image, into a 4x4 image, taking into account this kernel. So it is upsampled using a kernel. It is simply not upsampled by nearest neighbor. This kernel has an influence on how this image got upsampled. So that is transposed convolution, and we will see that this kind of upsampling is required in many encoder-decoder networks, and we will see some of those architectures in this course. So just to summarize, I want you to remember two things from this video. The first thing is that in a neural network, whenever you want to upsample an image or a feature map, one option to use is transposed convolution. The second thing to remember is that it is called deconvolution sometimes, but it is not deconvolution in the signal processing sense. But if you ever hear the term deconvolution used in the context of neural networks, you will know that it is transposed convolution. That is all we wanted to cover in this video. Thank you so much.